Okay, welcome back, everybody. So, we left off with a particularly good example of a quasilinear first-order PDE. So, our example was Berger's equation, or the inviscid Berger's equation. So, let me pull that back up. So here was the equation in question. All right, maybe I'll just rewrite that. So this is u sub t plus u sub x equals 0 with initial condition g. Okay, and we saw that what happened here was that unlike in the previous examples we'd seen, right, trying to go through this kind of in our usual way via characteristics, what happened was that rather than the structure of the PDE alone determining the structure of the characteristics actually depended on this condition, this auxiliary condition G. So we found that the solution was constant along characteristics. The characteristics were straight lines, but the characteristics were straight lines that had slope determined by this value, right, on the t equals 0 axis, right, the x-axis here. And so in our picture, if I had chosen a g that was increasing, maybe my characteristic picture would look like this. But if I chose a g that was decreasing, so say like, you could think of this being a choice of like g of x is equal to x, for instance. And so what happens when g of x is equal to like minus x or is decreasing, you get something like this where characteristics actually collide. I'm not saying that this is exactly what that picture looks like for the examples that I gave, but something like this is going to occur necessarily, right? You're going to have some points of collision between these characteristics, and why is that a big deal? The reason it's a big deal is because this is basically telling you that you have solution that is overdetermined in the sense that at a point here, this is a point that belongs to two different characteristic lines, and I know that the solution to this equation has to be constant along these lines. But these lines have different slopes, and so the constant that the solution is different along each line. So then at this point, the solution would have to simultaneously take on two distinct values, right? Which is not possible. I'm not happy having a multi-valued solution, right? That's not what I want. So this is bad for me, right? This is telling me bad things about a potential solution here. So let's actually go back and do a specific example for a specific g to show what it is that's actually going on here, right? So let's do an example of the Inviscid-Burgers equation where g of x is 1 if x is less than or equal to 0. It is 1 minus x if x is, say, between 0 and 1. And it is 0 if x is greater than or equal to 0. Or, sorry, greater than or equal to 1. Okay. Now, what does this look like? So, the plot of this is going to be, well, it's a constant 1. Right, if this is the t-axis, this is the x-axis. It's a constant 1 until x equals 0. And then it is the line 1 minus x, which looks like this, until x equals 1. Here's 1, here's 0, here's t equals 1. And then it is 0, right? So there's my function g. Okay. Oh, it's off screen a little bit. Okay. All right. So this is what my g looks like. Okay. Now, the question is, what does this mean for the characteristics? So just looking at this g, and going back to what I said previously about this, that I know exactly what is going on here in terms of the characteristics, right? Wherever g of x is increasing or, well, constant is fine too, of course, right? So I just want it to be non-decreasing, really, is what I care the most about, right? The slope is determined by g. If g is, like, say, strictly increasing, maybe it looks like this. If g is constant, of course, the slopes are going to be constants for those characteristics. So what should this look like? So here, since g is constant, the slopes of the characteristics are going to be constant at all points here, right? And so the slopes of any characteristics drawn for values of x less than or equal to 0 are going to be constant, having slope 1. And the characteristics for x greater than or equal to 1 are going to have slope 0. Now remember, this is slope 0 with respect to t. So this is, with respect to x, this would be infinite slope. These would be vertical lines. So when x is greater than or equal to 1, the characteristics are vertical lines. When x is less than or equal to 0, the characteristics are lines of slope plus 1, right, positive 1. Right? And so the only region where something else is happening is between 0 and 1. So if I draw this picture, so what do my characteristics look like? So let's draw the picture. So here is my x-axis, here's my t-axis. And so what is it that's going on? Any of the characteristics emanating from points like here, again, as I said, they're going to have slope 1. And maybe I'll draw one a little closer. In fact, maybe I'll even draw one at 0. Okay. So that's what those characteristics look like. Now, let's pick what happens at x equals 1. At x equals 1, those characteristics have slope 0 with respect to t, so these are vertical lines. So at any points here, characteristics look like this. If I extend these lines a little bit, of course, we see what happens is that the characteristics start colliding. Okay, so for instance, here the characteristics collide, right? Well, what about what happens in this region? Like if I pick something in this region, what is going to happen here? Well, if we think about what it is that's happening, right, at a point here, my slope is 1 minus x. And this slope is going to change. Right, this slope is going to change at these various points all the way up until x equals 1, where it has slope 0, all the way toward x equals 0, where it has slope 1. Right? And so what is it that is happening? What's happening is that these are, if here is like the level t equals 1, this is not exactly symmetric, right? Then what is going to happen? Maybe I should write it here. Let's not put it there. Let's put it here. It makes it look better. If here is height t equals 1, okay, what is happening is that if I'm drawing the line that has slope 1 minus x through each of these points, these lines are converging at this point where x and t are both 1. It's 0.11. Okay. So in this triangular region here, right, characteristics emanating from these points, if you think about them, they are at the point x naught and they have slope 1 minus x naught, right, passing through this point that determines these lines. These lines all look like this, and they're converging to this point where t is 1. Okay. Now, the thing to note, I'm going to draw a red line here. What does this tell us about how this solution is behaving? Right, how does this tell us about how the solution is behaving? Well, this tells us that if I were to, I'm going to draw a red line here, right, as like my cutoff. And if I were to take that and like cover this, right, I'm going to cover all that up until the red line. Okay. Then what is it that's going on here in terms of the characteristics? So if I cover all of this business, right, above the point t equals 1, I cover all of that, then each point on the t equals 0 axis, or the x-axis here, each point has a unique characteristic passing through it, and the characteristics don't collide, right? This collision doesn't happen until this red line. So if I cover this up, these characteristics don't collide. They completely fill out this strip, right, that I'm looking at. And so everything is good. And so theoretically, I should be able to write out a solution in the way that I've been doing this whole time up until this t equals 1 line, right? So if t is less than or equal to 1, I should be able to write a solution, right, that doesn't have any discontinuity. This discontinuity really should only arise at t equals 1. So we're going to see exactly how this works, but this is the key. Now, of course, after t equals 1, these things collide and the solution should be overdetermined. I'm not going to be able to write this thing down, but I should be able to write a formula for my solution so long as t is less than or equal to 1. Right? Because again, like I said, covering up this picture here, everything is fine. Right? They don't start colliding until this t equals 1 line. Okay. So let's try to do that. Right? Let's try. Let me go back here. Let's try. Let's try to write out solution u, supposing, right? So assuming t is less than or equal to 1. So I should be able to do this directly from g, right? So let me just rewrite g. G was 1 if x is less than or equal to 0. It was 1 minus x if x is between 0 and 1. And it was 0 if x is greater than or equal to 1. Okay. All right. So how do I do this, right? So now I know that u is constant along characteristics. So that's the first thing I know. Right? Now, you know, that is for this particular example. I'm not claiming that this is going to be true for all quasilinear examples. Remember, this is for this very specific equation. Okay. And so, use constant along characteristics. What next? So use constant along characteristics. The characteristics are lines having slope g of x naught. It's constant along characteristics. The characteristics are lines having this slope, but also u is this constant, right? So u is equal to g of x naught along each characteristic. So x naught tells you what characteristic you're on. Right? Once you know that, you have a point and you know the slope. G of x naught is the slope of that line, so you've completely determined the characteristic. Use constant along that characteristic, and u is equal to the value of that slope along the characteristic. Right? Okay. So we've seen from the picture that as long as we're assuming that t is less than or equal to 1, then everything should be good because these things don't start colliding until t equals 1. Okay. All right. So, how can I write out what U is? So, let's think here. Okay. So on this axis here, as we saw, let's go back here. If I choose points x naught that are like here, right, less than or equal to 0, the slope of the characteristics is 1 directly from this, which means the solution is also 1 there. And so u of xt is 1 when this is 1 if x is less than or equal to t, right? Okay. Well, what about if x is greater than or equal to 1? What does this picture look like? Well, let's go back here. If x is 1 or greater, what is it that's going on here? So if, like, say, this is my x naught, right? So this is my x naught, then what is it that's going on? Well, now my slope is 0 with respect to t, right? So the value that u takes along these vertical characteristics is 0. So this should be 0 if x is greater than or equal to 1. And so what do I get in the middle, right? In this intermediate region? Well, let's think, right? So I've done x is less than or equal to 0, and I've done x greater than or equal to 1. So in this intermediate region, when x is between 0 and 1, what is it that's going on? Well, this slope is going to decrease in a linear fashion from 1 to 0. All right, so slope decreases in linear fashion from 1 to 0, all meeting at the point 1, 1. So, i.e., compute slope of line. So from generic xt to 1, 1 with respect to t, but the slope of the line from 1, 1 to generic xt with respect to t is just 1 minus x over 1 minus t. Okay. And so this is 1 minus x over 1 minus t if x is between t and 1. And this is my solution. Remember, this is with the assumption that t is less than or equal to 1. I can't write out a formula like this without that assumption because of these colliding characteristics. Now, what I want to do is to show you a picture. And rather than take the time to draw it, the textbook has done a really good thing here by actually enumerating this. So let's have a look. So, okay. Here is the picture of the characteristics and how they collide at t equals 1. Below are solution profiles. So if I take this solution formula that I wrote just from the characteristic picture, knowing that it's constant along those characteristic lines, and it's equal to the slope of each line, and of course in the first and last region it was easy to see because those slopes were just constant in those regions, and the only region there was to determine something was this one. This is just the slope of the line connecting generic point in that triangular region xt to 1, 1. That's it. So, going back here, what happens for different solution profiles? T equals 0, this is actually what this is just the graph of G, right? This is just the graph of G. So that's my initial signal, if you want to think about it like that, my initial wave. At t equals 0.5, you see how this is like the top is sliding here. At t equals 0.75, it's sliding more. The slope of this line here is getting steeper, right, with respect to x anyway. Until at t equals 1, what happens is that this top has slid far enough right with respect to the bottom that now we have introduced a jump discontinuity, right? Now the textbook says the reader must see the direct connection between the plot of the characteristics from t equals 0 to t equals 1 in this figure, and these profiles do not continue until this is clear. That's a pretty good warning, just to let you know how important this kind of example is, because this is one of the best and clearest and most simple examples of where these sorts of discontinuities are introduced, and this is all due to the nonlinearity here. Okay, so here's the characteristics. We see they collide after t equals 1. We see what that translates to in the solution profile is a jump discontinuity here, right? So as t evolves, as t increases, this top is like overtaking the bottom until a break happens, a jump discontinuity. Any such discontinuity that arises like this will propagate to the right with a speed determined by the PDE. Okay. Such jump discontinuities like this are called shock waves, right? Or this is an example of how shock waves propagate. Okay. Now, recall our original motivation here, right? So recall our original motivation. We had looked at this, like the original transport equation. And of course we saw here that what happened is if we thought about this as a signal or a blip or whatever, we had some initial shape of this blip, this signal, and it propagated. Yeah, I drew it way too sharp there. It propagated, right, if this is here. Right? And this maybe is like this, and this goes here. It propagated to the right, right, at constant speed in this case, without altering the shape of this thing. We saw in the variable speed example we did that the shape was altered as it propagated to the right, but it was altered in a way that was not what we were trying to model with waves breaking, right? But in Berger's equation, or the Inviscuit-Berger equation. Right? In this case, what is it that was true? Right? So in this case, right, if we thought about this constant, so going back to this constant speed transport equation, we could think about this like the height of this, right? The value of, we'll call it the height, right? The value of this at your point, right? So the height, if you like, at a particular point there, okay? That height of this signal is being transported at constant speed here, right? Through one-dimensional space, right? With respect to x. So the height of the signal being transported. And in this case, that height was not altered, right? It wasn't altered, and the overall shape wasn't altered as this thing was transported. But then for Berger's equation, what does this mean? So here, this g of x naught, right, moved at speed c, right? Right. So this moved at speed c. But for Berger's equation, the initial signal moves at speed, well, it moves at speed, the value of the solution is the speed here. The value of the solution we know is constant along the characteristic line, so it's it's also g of x naught. So g of x naught moves at speed g of x naught. So this initial signal moves at speed determined by the height of the initial signal, i.e., the higher the signal, the faster it moves. I.e., the higher the value of the function, right, the higher parts of this graph of the function move faster than the lower parts. Right? So if you began with a solution profile that looked like this, right, then after some time, because the higher parts are moving faster than the lower parts, you get something that maybe looks like this, right? And maybe this keeps going, right? You get something that looks like, until it's almost vertical here. Until eventually what's going to happen is if you keep going, you're going to, I'm just going to draw something here, right? You're going to get something that's like this. But what's the problem with this? Right? This is bad news. Right? Because this is exactly, what does this mean, right? If I ask you to draw, like, you know, I took you back to like 8th grade or something and ask you what's the problem with this, you just say it's not a function, right? It fails the vertical line test. It's multi-valued here, or it's over-determined. What exactly is happening is that a jump discontinuity is being introduced here by the breaking of this wave. So to see a picture, or this signal, to see a nice picture illustrating this, right, here's the idea. A signal transported by Berger's equation looks something like this. The top is moving faster than the bottom. So for enough time, this thing will break, right, in the sense that eventually the top overtakes the bottom and it crashes over. Well, that's exactly what we were trying to model, right, when we first investigated this example. So that's, you know, a relatively simple phenomena that has like pretty complicated math behind it, right? That is, we have to be very, very careful with how we address things like this. This is a consequence of dealing with nonlinearity, right? Okay. So so a final thought before moving on to my general case. So final thought before general quasilinear statement. Um, for nonlinear uh, this includes quasilinear. It, you know, semilinear and linear, but even semilinear, even though semilinear is nonlinear, semilinear, this is also something you don't really have to worry about. But for fully nonlinear and quasilinear first order PDEs, the structure of the characteristics and the solution itself interact, right? So there is interplay between structure of the characteristics and the solution itself. So there's interplay between the structure of the characteristics and the solution itself. So we saw this previously, or I mentioned this in the previous lecture about how so in contrast, for a linear or semilinear first order PDE, I can determine the characteristics, right? I can determine the shape that they take without reference to the auxiliary condition, i.e., I can do it from the PDE alone. Now you might say, wait, if I go back to those examples, clearly that g of x naught like shows up in the solution. So what do you mean you can do it without the auxiliary condition? What I mean is that the particular choice of g doesn't influence what's going on with the auxiliary condition. So g can remain completely arbitrary in that sense. Whereas we saw here, we very much couldn't, right? It very much mattered whether or not we picked a g that increased or didn't, right? So the actual specific g that we picked allowed us to either be, happy and find solution, or told us that we wouldn't be able to write out a solution, right? So it's definitely different than the linear or semilinear case, okay? And this is just a consequence of non-linearity. Okay, so that's that. This is a very, very important example, so if you have any questions or you have any misgivings about the Berger's equation example, definitely review both today's lecture and the previous lecture and read your textbook. And once you see exactly how this interplay is working for that example, it will definitely help with a lot going forward, a lot of your intuition. Okay, and so now, what do we want to do? So now we want to talk about method of characteristics for quasilinear equations. Method of characteristics for quasilinear equations. Okay, so first of all, what is a quasilinear PDE? And we'll do this for two independent variables, but again, I'll do at least one example where we extend it and do it for more than two. So let's say we have two independent variables, x and y. This coefficient function, is now allowed to depend on x, y, and u. All right, times u sub x plus my second coefficient function, again, is allowed to depend on x, y, and u itself, times u sub y. That is equal to a third function, which is allowed to depend on x, y, and u itself. Okay. So we are given, of course, a, b, and c, and we want to solve this PDE in domain omega with data specified on some data curve gamma. Okay. So, again, we view this as a statement about directional derivatives, and from the exact same reasoning that got us the characteristic equations in the previous case. Our first characteristic equations look like this. Again, if we let our characteristics be parameterized curves, then the derivative of x with respect to that parameter is equal to the coefficient function on the x partial. So this is with the parameter s plugged in. So this is a of x of s, y of s, u of x of s, y of s. Yeah, that's enough parentheses. Y dot s is equal to b of x of s, y of s, u of x of s, y of s. Okay. Now, of course, like this is not going to be enough alone. We have at least one more equation, right? And this equation now, of course, can be simplified a little bit in form if we, just like we did before, define z of s to be the value of u along a characteristic. Okay. Then, in this way, our third characteristic equation is, of course, this derivative with respect to s of u x of s, y of s. I'm going to press notation to let myself, not go totally insane here. So this is x dot su sub x with the stuff plugged in, right? Y dot s u sub y with the same stuff plugged in. Okay, this is just me taking this derivative, chain rule, all that business, right? But by these previous characteristic equations, this is A and this is B, right? With stuff plugged in. I'm not going to rewrite all that. But of course, if I claim that this Z is going to solve this PDE, this is an important thing, and I'll go back to this. Before we move on after we've done some examples. It is kind of an important thing here that I've talked about before, where the logic here goes in the following way. I assume that a solution to this thing exists, and then I see what it has to satisfy. And you might say, oh, that doesn't actually prove the solution exists. But the way that we go about this is we assume that one does. We show like the thing that it has to satisfy in terms of these characteristics. And then this may allow us to justify the existence of solution when we can actually find it. You can think of it as looking at like candidate solutions, if you like. I'll return to that. Like I said, I'll kind of worry about the nitpicking there a little bit later. So after I've done a few examples. Um, so then this is a u sub x, b u sub y, which if this satisfies this differential equation, or sorry, yeah, this PDE, then this has to be equal to c x of s, y of s, u of xy, which is z of s, right? So putting all these things together, I get my characteristic equation. So putting all these things together and using better notation, since z of s is u along the characteristic, my characteristic equations are actually in a very nice, in a way that it's easier to remember than the previous case, the linear case. This is x dot is a, y dot is b with all of the characteristic stuff plugged in, and z dot is c with all the characteristic stuff plugged in. Okay, there's my characteristic equation. So those are pretty easy to remember. What's the difference between this and the semilinear case? In the semilinear case, the first two characteristic equations didn't involve a z, right? Only the last one did. Right, so that was the difference. Right, okay. So let's do an example. And why not start off with our favorite quasi-linear example, right? The only one that we've even talked about, Berger's equation, right? So example, Berger's equation. Okay, so Berger's equation is u sub t plus u sub x is equal to 0, and my initial data is given by g. Okay, so let's say that, so say I want to solve this on the upper half plane, i.e., we'll say that this is omega is the set of ordered pairs xt such that x is a real number, so x can be whatever, and t is greater than or equal to 0. Okay. Our data is given on the boundary of this, that is, it's given on this t equals 0 axis, right? Of course, this is definitely quasi-linear, right? It's quasi-linear. Let's just check to make sure that we know it's quasi-linear. So recall, quasi-linear is of this form. So the question is, what are a, b, and c here for Berger's equation? Well, my a is we'll let x be x here, so that we'll pretend this is written in the opposite order. We'll let b be the function on the u sub t term, and then c, of course, is the right-hand side. So this is actually pretty easy, right? So a x t u is, so this is the coefficient function on the x term, so this is just u. Okay, b of xtu is 1. That's the coefficient function on the u sub t term, so this is just 1. And the right-hand side function is 0, so c of xtu is 0. Okay. But then my characteristic equations are just x dot, y dot, and z dot are equal to a, b, and c, right, with those things plugged in. So what do I get here? I have, so my characteristic equations are x dot of s is equal to u, but this is, u is z here, right? So this is z s. Okay, I have t dot of s is equal to 1, and I have z dot of s is equal to 0. So these are three equations that are pretty easy to solve. So here, together with the initial condition that we want t to be 0 at s equals 0, right? So we want t of 0 to be 0. This implies that t and s can be taken, so s can be taken to be equal to t here. So actually we can change this, the parameter s into the parameter t. And so then, so taking that out, I have two remaining equations here, right? That is dx dt is equal to z, right? Z of t. And dz dt is equal to 0. Notice this is exactly what we got. We did this original Burgers equation. I'm actually going to bring that back. Let's see here. I'm pretty sure I have this lying around somewhere. Let me see if I can find this lying around. Yeah, here we go. Notice, what did we get when we originally considered Burgers equation? dz dt is equal to 0, and dx dt is equal to z of t. So we actually got these without directly referencing this process, but it didn't matter, right? So we still arrived here. Now, what are the initial conditions here? So x naught is just some generic x, so x of 0 is just my x naught. And z of 0 is going to be g of, so z of 0 is going to be u of x naught 0, which is g of x naught. Okay. So I know exactly what these solutions are to both of these things then, right? So z of t, so what are my solutions here? Z of t is the constant g of x naught, and my characteristic curve x of t is g of x naught t plus x naught. So then once I'm off the boundary, right, if I have t greater than 0, so given xt with t greater than 0 now, so this is, I'm drawing picture, right? I'm picking a generic point xt in the upper half plane, and I want to find the characteristic, which I know is a line like this, that passes through it, right? Okay, maybe it's a vertical line, maybe it's some kind of line. The idea is I want to find the characteristic that is the x naught corresponding to it. I've already found that s is equal to t, so that's not a problem. So I just need to find this x naught, right? I need to solve for this x naught in terms of x and t. So what do I know? I know that u of x of t is equal to g of x naught, where x minus x naught over t, this is solving here, right? X minus x naught, right? Normally, what would I do here in my characteristic process? I solve for generic point xt satisfies these equations that I've gotten for x and t. Here, t is equal to s, so I don't need to do anything there. So I have x is equal to g of x naught t plus x naught. So x minus x naught is equal to g of x naught over t, or sorry, times t. So dividing through by t, that's my g of x naught here, right? What is the problem here? What is the issue here? How do I solve for x naught? So quick question. How do I solve for x naught? What's the difference between an expression I got here and what I got in the linear and semilinear case? Well, the main issue here is that I get an implicit relationship, right? Before I got an explicit relationship, I could solve it and have to worry about anything. But here, I can't always do this. What does solving this mean? The answer here is it depends on g. And here is how you see the dependence on a particular choice of g arising in this situation. Whether or not you can solve this for x naught depends on what kind of function g is, right? Whether g can be inverted, for instance, right? So, in fact, we can only do this when g is non-decreasing. Now, of course, I'm talking about we can only do this for this specific example. I'm not saying that we can only do this in general when g is non-decreasing, right? Depending on the PDE, that might literally be the opposite. Okay? But for this example, we can only do this when g is non-decreasing. Okay. And so, for instance, say that g of x is equal to x. Okay. Then, according to this, let's flash this back, or here, maybe I'll just move it down. Okay. So if, there we go. It's curling up a little bit. Oh, okay. Here we go. All right. So if g of x is equal to x, then u of x of t is equal to x naught, right? Where x minus x naught over t is equal to g of x naught, which is x naught. But I can actually solve for x naught here. This implies that x naught is, what, x over t plus 1? But if x naught is x over t plus 1, this implies that my solution, u of x of t, is x over t plus 1. And you can check that this actually is a solution to the PDE and the initial condition on the entire upper half plane. So we can check. In fact, you should check that this is indeed a solution to the PDE plus auxiliary condition on the entire upper half plane. But if instead we chose g of x to be minus x, then we would find, so you can do the same sort of analysis, that the solution corresponding to this should be minus x over 1 minus t. But this solution is not defined on the entire upper half plane. This is only defined on a strip. But this solution is only defined on the strip that consists of all points xt such that t is greater than or equal to 0 and strictly less than 1. In fact, at t equals 1, what do you think happens here? Well, you could say this thing blows up, right? At t equals 1, it's not defined. What happens? Right? The characteristics collide and a shock discontinuity develops. So I chose g of x equals x. I got a solution on the entire upper half plane. I chose g of x equals minus x. I got a solution on a strip, but not the entire upper half plane. Right? That's key. That's key because this shows us what's going to happen in terms of kind of the best that we can hope for when it comes to existence theorems. So we're not going to be lucky enough to get global existence uniqueness theorems like you do in ODE. It's just not going to work like that. So the way that this works then is instead, right, the best we're going to hope for is under the right conditions, we can get a local existence, meaning that in a neighborhood of the data curve. So this strip is a neighborhood of the data curve. The data curve here is just the x-axis, right, or the t equals 0 axis. So what we got was not the existence of a solution on the entire domain that we sought. Instead, it was the existence of the solution on a neighborhood of the data curve. Okay. So under some assumptions, we're going to be lucky enough to get that. Okay. So this shows how following this process leads to the resolution, or to at least showing that for Berger's equation, it is absolutely going to depend on the data function g, whether or not you can actually solve this. Okay. All right, let's do another example. Let's consider the PDE that is x plus u times u sub x plus y times u sub y is equal to u plus y squared. Okay. And let's give condition when y is equal to 1, u of x1 is x. We seek a solution on the domain omega which is the set of points x, y, such that y is greater than or equal to 1. Okay, so this is just the upper half plane shifted up 1. Okay. All right. So this is definitely quasi-linear. Now you might say, well, what is fully nonlinear, right? If these last few examples are quasi-linear, and we showed that they were of that form, let's go back to our, where did I put it? It's over here somewhere. Maybe we have a hope that we can find this thing. It is possible. Well, where did I? There we go. Okay. All right. So here's a quasi-linear equation. Okay. Now, you could say, well, how going from here, what's the more general thing? Notice the things that are left untouched in this are the partials themselves. So being fully nonlinear means that the function defining your PDE not only involves the independent variables and the solution itself, it also involves the partials. That's what it means to be fully nonlinear. And that's a nastier thing. It is a nastier thing to involve the partials. Here the partials are at least untouched. They're always kind of they're sitting there to have coefficients on them, right? But for a fully nonlinear thing, all bets are off. You can have the x partial of u to the 17th power and the y square root of the y partial of u, something crazy, right? So that's the idea here. Okay, so we seek a solution on this specified domain. So this is definitely quasi-linear. What is my a, b, and c? So a here is x plus u, b is y, and c is u plus y squared. If it wasn't already given to you in this form, you should put it in that form, but I'm not going to, I trust your algebra skills. I'm not going to try to trick you too much as far as that goes. So my a is a, x, y, u. This is x plus u. And b of x, y, u is y. And c of x, y, u is u plus y squared. Okay. So then what are my characteristic equations? So characteristic, the first one is going to be x dot of s is equal to x of s z of s. Okay. The next one is going to be y dot s is equal to y of s. Okay. And the last one is going to be z dot s is equal to z of s plus y squared, right? Y of s squared. Okay, so how do we go about doing this? There's no general process here, unfortunately, right? This is going to be completely determined by the form that these things take. So you look at this and you say, okay, well, here this one's clearly the easiest, so I should do that one first. Okay, so that's my process here. I try to find the easiest one first. If there's not some easiest one, then you're kind of probably in trouble, and hopefully there's some kind of algebraic trick you can do to make your life easier. But anyway, this is what I'm going to do. So this one is easiest, so we do it first. So first of all, how do I do this one? I can go ahead and write out the initial conditions here. So what are my initial conditions? My initial condition for this one is I want y at the s equals 0 parameter value to be equal to 1 here, right? And I want x at the s equals 0 parameter value to just be like a generic point x naught. And then z of 0 is going to be u of x naught 1, but by the auxiliary condition, this is x naught. So these are my ODEs, and there's the initial conditions for them. Okay, so this first one, I have y dot is equal to y, and y of 0 is equal to 1. So that's nice. I can immediately say that this, here, we'll do this. So take this one, move it out over here. I can immediately say y of s is equal to e to the s, because I've imposed the initial condition. So I found that my constant here is just 1. Okay, because of this, right? So y of s is e to the s. Okay. Now what do I do? So I have 2 left to do. You're looking at these and you might say, well, this one actually looks easier because this one has a nonlinear term in it. But actually, this one involves a z, which I haven't solved for yet, whereas this one involves a z and a y, but I just solved for y, so this is clearly the thing to pick here. So this implies that z dot s is equal to z of s plus y squared is e to the 2s, right? This is a first order linear ODE in independent variable s. So ODE solve via integrating factor. Right, if you need practice on that, you should look up integrating factor method or integrating factor formula, even if you just want to remember the formula. And this implies from ODE theory, z of s is what this is, like some constant, I'll just call it big C here, e to the s plus e to the 2s, our particular term. Okay. All right. Okay. Now, of course, imposing initial condition. So imposing, I see z naught, or z of 0 is equal to x naught. This means that actually I can determine this big C to be x naught minus 1 is what I get. Okay, there we go. Oh, I was off the page there. There we go. So imposing initial condition z of 0 is equal to x naught gives me, I can determine what this big C is, and it's x naught minus 1. Oh, wait a minute. E to the s. There we go. Now we have a hope of this being correct. Okay. So, now what? Now I can finally solve this last ODE, right? Now I can finally solve the last ODE. So now I don't know what x is, but I know what z of s is. So let me x dot of s is equal to x of s plus z of s, which we just found to be x naught minus 1 e to the s plus e to the 2s. Okay. I can also use integrating factor again and our initial condition. Remember, our initial condition is x of 0 is equal to x naught. So again, solve via integrating factor. And this gives me solution. X of s is e to the 2s plus x naught minus 1 times e to the s times s plus 1. Now, let's put all of this together. So now, given xy with y greater than 1 because we're in the upper half plane shifted up 1, right? We want to solve, so we want to find x naught and s corresponding to the characteristic passing through xy, what we always did. It's just now our equations, let's revisit this. So our equation for x is e to the 2s plus x naught minus 1 e to the s times s plus 1. Y is e to the s. I think I can sense where we're going to start here. And z is x naught minus 1 e to the s plus e to the 2s. Okay. So we need to solve for s and x naught here. So firstly, we solve for s pretty easily. So if y is equal to e to the s, then s is equal to the natural log of y. So that's easy. For the algebra I need to do now all I need to do is put in log of y here. So this becomes e to the 2 log y is the same as e to the log y squared. So this would be y squared plus x naught minus 1. E to the log y is just going to be y times log y plus 1. So what looked pretty horrible to solve for turns out to be this thing. We're solving for x naught here, so I don't mind. All we have to do is, yeah, let's go ahead. So let's move y squared over, so this then x minus y squared is equal to this whole thing, x naught minus 1 y log y plus 1. So I divide by y log y plus 1 and add 1. So x naught is x, so it's I'm adding 1, right? So it's 1 plus x minus y squared over y log y plus 1. Did I divide by that here? Let's see. So this is subtract y squared here, divide by y log y plus 1, and add 1. Yeah, okay. Let's see, e to the log y. Yeah, that's y. Okay. Log y plus 1. Yeah. There we go. All right. And so what is u of xy? It's z with these things plugged in. So this would be what here, this would be y squared. And this would be like x minus y squared over log y plus 1 plus y squared. Yeah. Okay. Sorry, I was off the screen there for a second. Okay. So first of all, you see that like this is you can check that this actually solves the PDE on the region in question, but you can check that this is getting to a point where in order to have any hope of doing this, this was all chosen extremely carefully, right? So this was all chosen carefully. This is kind of a caveat going forward for a lot of these problems because the resulting ODEs could be really bad. Um, so rather than focus on how bad they could be, we're gonna make them interesting but still nice, so that you actually have a hope of being able to do this and being able to find these nice closed form solutions. That's the good stuff. That's our main hope here. Okay, so this one is a particularly nice one just because a slight alteration in a few of the either a couple of these coefficients or in the data itself leads to some pretty interesting problems. So maybe that will show up on your next homework. Who knows? Let's do one more example just to put to bed what happens. So quasilinear. This is an example for quasilinear more than two independent variables. We do the exact same thing that we did previously, right? So let's look for a PDE that solves the following. So we're looking for a solution that is like u of x, y, t, right? Where u sub t plus u sub x plus t u sub y is equal to y. Okay, and say u of xy0 is some function, let's pick x. Okay. And we'll do this on the domain omega, which is xyt such that t is greater than or equal to 0. So this is upper half space, right? Now, maybe I should put quotes around this because, of course, t is our time thing, so it's not a spatial thing, so maybe it feels weird to call it upper half space, but just like we called it the upper half plane and the xt plane, it's the same kind of thing, right? We don't care. All right, so again, because the leading coefficient of the u sub t term is 1 in the characteristic equation for t, I get, and because this initial t is 0, I get that s is equal to t right off the bat. So I can parameterize all of these in t if you like. What do the characteristic equations become? The one for x is x dot t is u, which is z, right? Y dot t is t, and z dot t is y. Now you might notice that, oh, hey, that's kind of a neat thing. Even though this is an example of having more than two independent variables, because the leading coefficient here was 1, actually it just means that I can parameterize, instead of parameterizing an s and having an extra characteristic equation here, immediately I get that I can actually parameterize by t instead. And so this actually reduces, in a sense, to the characteristic equations that we're used to, which is why we didn't even need to change our notation here, right? We didn't have to change the labeling of the independent variables. So that's nice. Now, what are the initial conditions here? So the initial conditions would be we want x to be generic. So x of 0 is x naught. We want y to also be generic here. So y of 0 is y naught. And z of 0 is, of course, the auxiliary condition here, which is x naught. Okay. So solving the y equation, this is actually just an explicit ODE. I can just differentiate, or sorry, I can integrate and impose the initial condition to get that y of t is what? This is just t squared over 2 plus y naught. Right? That's a differential equation even a calculus student could do that never had ODE, right? Okay. Then what about the z equation? Now that I have y, I can solve this z equation. So similarly, now this is now also an explicit ODE. So z of t I can obtain just by directly integrating. And again, I get that this is t cubed over 6 plus y naught t plus x naught. Hey, this isn't so bad after all, right? So then given, oh, well, before I do that, obviously I have to solve the x characteristic equation. So now I know what z is. So if x dot is equal to this, well, I can keep going, right? This implies that x of t, again, is actually just an explicit ODE. So I can integrate again, and I get t to the fourth over 24 plus y naught t squared over 2 plus x naught t plus the constant term is x naught because of that initial condition. Now you can check algebraically, right? So given and completely generic xy and t greater than 0, we can solve for x naught and y naught. So x naught is, solving for x naught here, I get x minus t to the fourth over 24 minus y naught t squared over 2 all over t plus 1, and using the y expression, of course, y naught is equal to y minus t squared over 2. So I can plug this y naught in here to get an expression that only involves x, y, and t. And so that's exactly what I'll do using z here. So then this takes a little bit of algebra. You can check. So check the algebra. U of x, y, t can be found by doing what? Well, I have an expression in z for x naught and, or that includes x naught and y naught. All I need to do is sub those things in, right? And of course, x naught depends on x, t, and y naught, but y naught just depends on y and t. So subbing that in here for x naught. All of this stuff yields the following, which is 24x minus 12yt squared plus 5t to the fourth all over 24 times 1 plus t plus yt minus t cubed over 3. This is one form you could write it in. Okay. If you really feel like it, you could, of course, check that this actually does solve the PDE, but you might want to use like an algebra package to do that if you don't want to, you know, try to feel good about yourself by doing it by hand and then cheering that you did it by hand. Anyway, that's a pretty good stopping point here. Now you've basically seen a handful of examples for quasilinear equations. I'm going to go over some notation for the fully nonlinear case. I will do an example or two of the fully nonlinear case after I state the characteristic equations. And that will be, after we kind of tidy up some intuition and stuff, that will be most of what we do for first order. So we'll finish our discussion of first order equations during the next lecture, and we'll move on to the 1D wave equation after that. So we'll be moving into the second order realm. But anyway, I'll post your second homework later today. So be looking for that. I'll make an ELMS announcement when I do. So anyway, that is that, and I will see you all around.